Hello, my name is Dylan Walters, and this is my Rijke tube slide report for Lab 4. So for some background on our lab, the purpose of this lab was to analyze the combustion dynamics that occur in a Rijke tube. The Rijke tube is a long tube that is open on both sides. There is a Bunsen burner that is placed at the bottom of the tube, which applies the combustion reaction. Throughout the reaction, the velocity and the pressure inside the tube oscillate, and these two cycles continuously feed each other and grow until resonance is achieved. During this lab, we were also introduced to new equipment such as a photomultiplier and a piezoelectric pressure transducer. Both of these equipments will be discussed in the following slide. So our main piece of instrumentation was obviously the Rijke tube, which we used in the ESM building. In order to gather data, we used a piezoelectric pressure transducer, which measures the pressure fluctuations at 3 different locations in the Rijke tube. When a strain is caused by the pressure, the crystal inside the transducer produces a current, which can then be measured. We also used a photomultiplier to measure the reaction rate during the experiment. The photomultiplier examines a specific range of light wavelengths, which was targeted for this combustion reaction. The combustion reaction then produces chemiluminescence, which is recorded by the photomultiplier and is able to give us information on the reaction rate. This slide shows the setup of our experiment. The picture on the left shows the Rijke tube when lit. The picture in the middle is of the control stand, which we use to ignite the tube and to measure fuel flow. The picture on the far right shows a more complete view of the Rijke tube. You can see the fan at the bottom of the tube and the measurement stick that we use to determine different locations on the of the Bunsen burner. And then not pictured on this slide, there were tanks of propane that were open and closed using a lever in order to supply fuel. That pretty much consists of our experimental setup. So for the procedure for this lab, the first step was to record measurements of the Rijke tube length and location of the pressure transducers. These measurements were later needed for data reduction. The next step of the process was to allow fuel to flow and ignite the Rijke tube to begin the experiment. We performed the experiment at 4 different burn locations. The first 2 locations were predetermined to be at 0 and 2 inches. The third location was at the height that resonance ceased at, which ended up being 4.5 inches for us. The final location was the height at which resonance began again, and this location was 1 inch under the initial 0-inch location, or -1 inches. At each burner height, we collected pressure data using a computer so that we could have some analysis on our Rijke tube experiment. So here are results from the data we collected. This slide shows the amplitude in decibels and frequency in hertz of each pressure transducer at each burner location. The RMS voltage and frequency of the PMT is also displayed. These amplitudes were calculated by converting the voltage to PSI using the figure provided in the lab report. I then used the formula shown in the bottom right of this slide in order to calculate the amplitude in decibels. The chart also shows, it clearly shows that resonance was achieved in the first, third, and fifth trials. You can see this closed trial was actually the first one, but every trial where there is a resonant frequency of around 97, it's where resonance was achieved. And then for the 2 trials where it was only 1 in terms of frequency, that's where resonance was not achieved. We also calculated the theoretical frequency on this slide, which came out to be about 94.6 hertz. And so that is clearly relatively close to the actual values that we measured. So that is always a good thing. We also determined the relative phase angles of peak frequencies for each pressure transducer at the 0-inch location for our data reduction. The examination of the relative phase angles helps us to better understand the fluctuations that occur in the Rijke tube. There's obviously a clear difference between the phase angles when resonance occurs and when it's absent. As you can see, the P1, P2, and P3 are all very close when resonance occurred, and there is a lot of fluctuation or a lot of divergence in the open case where there is no resonance. So for conclusions, this lab was definitely the most interesting lab that we conducted, in my opinion. It was clear that there were specific conditions that create resonance. First and foremost, a fan is needed at the bottom of the fan to produce initial velocity in order to start the fluctuations of pressure and velocity and get the entire reaction going. It is also apparent that the tube cannot be open in order for resonance to occur, as it did not occur when when we opened it, and also when the burner was placed too high. Um, the Rijke tube is an important phenomena for us to understand because the fluctuations in heat release, velocity, and pressure lead to a better mix between the fuel and the air needed for the combustion reaction. This better mix in our fuel in turn leads to a higher combustion intensity, which is very important. Another benefit of the pulsations is that it pushes the byproduct of the combustion reaction out of the Rijke tube, which again improves our engine efficiency. So the Rijke tube is a very good model for pulsation engines that are very efficient. Thank you very much for paying attention to my presentation.